We go. All right. Good afternoon, everybody. Today's seminar is by David Murphy, Professor of Environmental Studies at St. Lawrence University. He focuses on the intersection of energy, economics, and the environment, very much in the interdisciplinary spirit. And really, his research, if you look at it, is first of all very interesting, and secondly, really looks at a broad variety of questions that really brings the spirit of ecological economics together and bridges disciplines. Uh, for example, he looks at economic growth and environmental damage and how that's connected, and also how renewable energy is used to uh, be a transition away from fossil fuels. So a lot of Dr. Murphy's work is in life cycle analysis, and he looks at the energy and environmental cost of energy technology and systems. And we are very, very fortunate that he's here today. And really, thank you, Dr. Murphy, and we'll turn it over to you.
Well, thanks, John, for that introduction, and thanks everybody for attending. I was really excited when John reached out to set this up, and mostly because it's been a little while since I've spoken or presented with USSEE. So I was excited to get back with this community. I'm going to share my screen. I'm not the best at like I would, if you have questions, I want you to feel free to ask them during the presentation. But obviously on Zoom, it's hard sometimes, and I don't always see like the hand raise or anything. So feel free to shout out and just interrupt if needed. I think we'll have time afterward, or John, if you see something, feel free to say something. But let me share my screen first and make sure we are rocking and rolling here and everybody can see everything. So let me start the presentation. So did that share with you all?
Yes, it's perfect. And
Okay.
I'll monitor the chat for you.
Yeah, thank you very much. I think there's probably a way to hide this thing. Hide video, hide floating meeting controls. That's what I want to hide. Okay, perfect. Um, all right, so the presentation I'm giving is called Harmonized EROI Estimates and What They Mean for the Energy Transition. I've been studying energy return on investment since my PhD, basically with Charlie Hall, who was the originator of the term. And this area of work has grown a ton in the past, probably 5 or 6 years in particular. And the research I did in the harmonization paper in 2022 is eventually what we're going to talk about in this presentation. But I wanted to kind of just set the stage a little bit for a few minutes. And I'm going to start just by kind of reviewing what energy return on investment is, right? So EROI is a profitability measurement. It's kind of akin to financial return on investment. An EROI is usually it's a ratio, right? And we usually say, let's say 10 to 1 means for every 1 unit of energy invested in an energy extraction process, 10 are produced. And importantly, net energy is related to this, right? The net energy from that process would be 9 units in this example. So just so everybody knows what we're talking about, this term originates from ecology, really. Um, and it was actually in Charlie's thesis. He dealt with trout, but I feel like this image of the cheetah is easier to understand, right? And the idea is very, very simple, right? Basically, the cheetah must gain enough energy from its prey to pay for its own metabolism, and certainly at least pay for its metabolism and extra energy, that net energy, if the cheetah wants to grow or reproduce or do anything like that. So the energy return on investment, in other words, for an organism has to be greater than 1. And we can see this in our own bodies, right? As I get older and my metabolism slows down, right? It's really easy to put on net energy, right? And to grow in ways that you don't necessarily want to grow. But my research really takes this concept and applies it to society and to economies. And you can see the picture here on the right. This is my picture of what the economy is, right? Which is a bunch of cars on the highway, a gas station in the corner, and you can see kind of energy consumption all over this, right? There is a metabolism to the economy. The economy cannot run without energy, so the energy sector has to supply the economy with energy all the time in the form of liquid fuels, gasoline, and electricity, just to keep the metabolism running, right? And if we want that economy to grow, right, to add new buildings, new cars, we need more net energy, right? We need even more net energy to pay for the metabolism, but then also to add to growth. All right, so that's why EROI is important, at least I think. So the economy's kind of like a cheetah. So how does EROI impact society? Well, it's good to look at this through a hypothetical, all right? And we could look at an oil economy on the left here, and what happens if we transitioned all of our liquid fuels to biofuels? Well, and this is a very simple diagram here. On the top, we have an oil economy. Let's say this oil economy has an EROI of 18, okay? Um, and we say we extract 100 units, and that extraction process costs 6 units, right? Well, we get 94 units for society, and that's the net energy that's left over, right? Um, if we transition to a biofuel economy and we have an EROI of 1.2, right? That same 100 units delivers 20 units to society. And because 80 units have to be used in this extraction process. All right. And I like this quote from Howard Odum, who is the advisor of my advisor, right? So part of the Odum tree here, and who said in 1973 that the true value of energy to society is this net energy, which is that after the energy costs of getting and concentrating that energy are subtracted, right? So what we're after is the net energy, and EROI is a ratio, this unitless ratio that kind of indicates how much net energy is being produced, right? Whereas net energy is kind of just a subtraction of those two things. So high EROI equals kind of high net energy. But it's really, really important that we understand that these two things are related non-linearly, all right? If we look at the graph here on the right, this is often referred to as the net energy cliff graph. What we're looking at is energy return on investment on the x-axis going in kind of reverse order. So we have 50 on the left all the way down to 0 on the right. And on the y-axis, it's net energy fraction of available energy. So remember in that graph I showed you, or the figure a couple before, where you pull out 100 units and 94, I think it was, were delivered. That 94 net energy is all this purple. That's that fraction of all the energy that's extracted. So one would be 100% of energy extracted. What percentage of that is delivered to society as net energy? And you could see a couple things here, right? Let's kind of pick this apart, right? The first thing to note is that there are very marginal differences in net energy given changes in EROI that are above 10, right? So you can go from 50, which delivers 98% net energy, all the way down to 10, and the reduction in net energy to society only changes from 98 to 90, right? Very marginal differences. Reducing EROI from 10 to 5 then changes it from 90 to 80, and then reducing it from 5 to 2 now changes from 80 to 50%, right? So what are we saying here, right? What's the takeaway message? The takeaway message is that when we think about EROI, right? EROI is a ratio. What we're interested in are those net energy flows. That's what's going to impact society and whether or not society can thrive or will have to shrink. And really what we're trying to do is avoid very low EROI resources. We think about this threshold of 10. I don't know that it's 10. 10's just kind of like a round number. But 7, 8, 9, 10, 11, somewhere in there, right, is where that drop off occurs. And somewhere in there, is the threshold of where we want kind of to avoid, right? So we don't want resources that are super low. But the flip side of that is that it matters much less whether whether a resource has an EROI of 50, 40, 30, 20, 15, right? because they all provide a lot of net energy to society. So the value of finding resources that have EROI of 100 are less important than just avoiding resources that have EROIs of like 1.3 to 1. Okay, so in sum, EROI is a measure of energy profitability. Net energy is what society wants and needs, right? EROI is related to net energy nonlinearly with the threshold around 10. The big question, right, in the literature that has tried to be addressed over the last decade, I would say, is that does the energy transition in general threaten the flow of net energy to society, right? Is this a problem? And is this something that we should be worried about? And really, what we're thinking about here is what are the EROIs of renewable energy resources, right? Are they high enough to maintain those net energy flows to society? In other words, are they above the threshold? So let's look at the literature, shall we? So this is a paper I published with Charlie out of my PhD dissertation, actually, back in 2010. And it summarizes a lot of the information that was in the literature at the time. And we can see average EROIs for oil, imported oil, natural gas, coal, tar sands, shale oil, all these things. I just average them there because it's hard to read a table. It's got so many numbers on it. It's about 22, right? Nuclear's somewhere between 5 and 15. Wind is about 18. Solar 3.5. Biofuels are 1.2. Okay, so this would indicate that solar could be problematic. Wind is okay. Nuclear, depending on which estimate's correct, somewhere in there. And fossil fuels are fine. This is another graph that Charlie's put together a bunch. This is called a bubble graph. You know, on the x-axis here, we have the size of the resource, which is also supposed to be indicated by the size of the bubble too, versus EROI. And we could see, you know, so this is U.S. consumption over here. That's just to show everybody how much energy we consume. But, you know, so we have imported oil, domestic oil, natural gas. This is an old graph. Coal, domestic oil, nuclear. Down here we have tar sands, biofuels, solar, wind, right, somewhere in this area. So kind of echoing the last research we saw. Hydro has a huge gap here, depending on the or huge range, depending on the type of hydro facility it is, I suppose. More recent literature. So this is literature that was published in 2016. An electrical supply system based on today's PV technologies cannot be termed an energy source, but rather a non-sustainable energy sink or a non-sustainable net energy loss. It's Ferroni and Hopkirk in 2016. So that indicates that EROI of solar is less than 1. Rouget and Lestesi in the same year calculate that in the UK, coal EROI is 10, PV is between 10 and 25, gas is 41, onshore wind is 50, etc. So those kind of give starkly different estimates for PV, right, and other resources. And we have work by Brockway et al. This was in Nature Energy in 2019. They calculate something called primary, EROI primary energy over here. And they have coal, what is this? This one's coal, this one's oil down here, and we have gas in here as well. And you can see that in 1995, there's a bit of a range, and they kind of unify down here in 2011. This green line is EROI final, much lower, and this is kind of the final estimates they put together, blown up. And you can see that these are pretty stationary, but the magnitude is much different, right? These are all now below 10. So different estimates there, right? This is a figure I published in 2011. I think you're getting the sense of what I'm doing here, right? Which is showing you all these various estimates that are out there in the literature. Historic oil and gas fields, right? This is the net energy cliff, but I'm just going to use it for these EROI estimates, right? Oil and gas is here. New oil and gas is a little bit lower. Solar PV, we just put this huge range on. Wind has a huge range. Nuclear, sugarcane, ethanol, tar sands, and temperate latitude biofuels are over here. Whew. Okay, so one more. Hall and Day in 2009. This was published in American Scientist. Right? These are different EROIs of various resources. Okay, photovoltaics are over here, nuclear is here, domestic oil domestic oil in 1930, so older. So there's temporal differences on this graph as well. I forget why some of these are colored light green and dark green. I think it's like variability in the estimates. So like coal could be 40, but it could be 80, but I'm not sure about that. Um, so what is the EROI of each energy resource? You know, like that was just those were literally the estimates because I was putting this talk together. Those were just the ones that I know the most because either Charlie published them, I published some of those. They're papers that I've written or been involved with in the past. I could have spent hours putting together another 100 slides of estimates of resources that are out there, and we would get no closer, right, to consensus on what the EROI of these resources are. There's just been a total proliferation in literature, right? And I guess I would say that, like, to answer this question, what is the EROI of each resource? Well, spoiler, there isn't one answer, right, for each resource. And we can probably put ranges, but there probably shouldn't be a point estimate, right? And there's good, I think, rationale for that. First of all, there's geographic variability, right? This is just the insulation of the US. So I'm in way upstate New York, almost in Canada, basically, and my installation here is going to be what, a third, a quarter of what it's going to be in the desert Southwest, maybe a fifth or an eighth. So if we think about photovoltaic panels, obviously energy out is the numerator. And we're going to have massively different energy out. So that's going to mean energy EROI differences. There's also temporal variability. And this is the effects of technology and depletion, right? This is oil production in the early 20th century. This is oil production in the early 21st century, okay? Vastly different technology, right? To access resources. The one on the left is plunging into a salt dome couple thousand feet under the earth. The one on the right is plunging 10,000 feet through water to hit a hole in the ground and then going 15,000 feet beyond that. Vastly different technology, vastly different depletion, right? So the EROI should change over time. And there's resource variability. This graph alone, right? These two are crude oil, right? A liquid fuel. They're also natural gas. Now we have a gaseous fuel and crude oil together. Solar PV and wind are electricity, okay? Tar sands is another liquid fuel, so that's crude oil. Nuclear, depending on whether we're thinking of uranium, the primary energy source, it could be there, or it's electricity. And then these are ethanol, okay? These are liquid fuels, and they're energy carriers. The point being that these are all different sources of energy. These ones up top are primary sources of energy. These ones down here are energy carriers. Primary sources of energy are the sources of energy that we get from nature, right? And energy carriers are ones that have been transformed from nature to some other form. So like electricity is a good example of an energy carrier because it doesn't exist in nature, right? We have to create it from some primary energy source. All right. So the question is, how do we make sure that EROIs are commensurable, right? That we can look at them and make comparisons. And that's really what's plaguing, I think, the net energy literature right now is like, there's a lot of analyses going out there, and there's a lot of them that are being compared, including the work I showed you earlier, that are making kind of like inappropriate comparisons. So let me discuss the evolution here. So in 2016, I started working with some other scholars and friends that did life cycle analysis. Now I was very much my PhD was in environmental science, but it was based in biology and ecology, and that's kind of like where my home was. So I didn't come from an LCA or an engineering background like some of my colleagues were. And so when we started putting together this 2016 paper, because this issue of comparing EROIs has been out there for a long time now, and we wrote the paper on the bottom here, why the net energy analysis community needs to adopt the life cycle analysis framework, because I was really blown away by how uh, what LCA enabled me to do, right? It was one of these things. I don't know if you've had this experience in your own research, but it immediately elevated, I think, the rigor of the work I was doing and allowed me to do a lot more with net energy analysis. And I'll go into why that's the case in a few slides. But this is kind of the evolution. So like these two communities kind of evolved a little bit separately. There might have been a little crossover, but kind of simultaneously. And what's interesting to me, right, and this is just a timeline with some of the various kind of larger publications on both sides of it, for both communities. But the LCA community emerged and developed in 2006. You can see the ISO standards. So they have a standardized, globally recognized methodology in the ISO 14040 and the ISO 14044 documents, right? So this is a standardized methodology that everybody in the world can use and should use. And it's got some rules associated with it about how to do comparisons. And the reason that emerged was that the literature was replete with estimates of LCAs for similar products that were coming to vastly different conclusions, right? So they had this commensurate, the same issue that the net energy analysis community is having a little bit, right? This idea that like you could do the same, a similar analysis for PV and get two wildly different EROI estimates, right? So what they wanted to do is develop a way where they could allow for flexibility in analysis and allow analyses to go forward and be designed and be bespoke and idiosyncratic and unique to whatever the problem is that is being identified, but still have a methodology and steps that could be followed. So that if somebody else wanted to do something similar, they could. And that's how LCA emerged. And that's where I came in 2016 writing this paper, because the EROI community was having the same sort of issue. And I don't want to like sound as though LCA has solved all the work. There's still a whole host of issues with LCA work, and there's still a lot of estimates out there of products that are the same product that lead to different conclusions, right? It hasn't solved the problem, but I think it is reduced the issue quite significantly. And that's where I think the net energy analysis can benefit. So let's do like a 2-minute review of LCA just for people. I'm sure there are people on the call that have never like looked at an LCA book before or anything like that. So I don't want to take anything for granted. Just know that what I'm summarizing here has like entire grad programs and undergrad programs. So I'm very much doing just a 2-minute review here real quick. So the first thing we identify in LCA, right, is that this is an iterative process. Here's the framework on the right. So the first thing you're supposed to do is define a goal and scope, and we're going to talk about that in a second. The second thing you do is collect your data. They call it an inventory analysis. And the last thing you do is assess the impacts. And at every stage, there's an interpretation. Oftentimes, this has happened with me a bunch, right? You set a goal and you scope it out. You go and collect your data and you realize your original scoping can't be met, or you have more data, rarely, but like sometimes you get more data than you realize, and you can expand your scope and do more. So you go back, you redefine your project, and you work through. Importantly, what LCA does is define some rules for comparative assertions, they're called, right? So what do we do? How do we make sure that when we do an analysis of a product, right, and we compare it to another product, that's a commensurate, right? That those two things are commensurable, that we can actually compare them. And what they say is basically you need to ensure that the study design parameters of these analyses are the same. There's a whole bunch of study design parameters. I think the three that are most relevant are the goal, and then in scoping, the functional unit and the system boundary, right? If the NEA community can get these three kind of like together and utilize these three, we'd be it would kind of advance the literature, I think, even further from where it is today. So what is the goal? The goal basically is you're stating your intended application, the reasons for carrying out the study. This is all in textbook. This is straight textbook material. The audience, whether the results will be used in a comparative assertion, right? So stating up front whether or not the goal, and that I think is important because there's been a number of papers that will do an analysis of one thing, but then in the conclusions conclude that because they calculated X, the comparison of X against all Y and S and all these other technologies, and then make some grander conclusion, right? Well, if the goal is to do that, to say that, to make a comparative assertion, then we should think about how to structure the analysis differently. Um, the functional unit and the system boundary are the next ones, right? So the functional unit defines the unit of analysis for an LCA. 1 kilowatt-hour of electricity, 1 megajoule of gasoline. And the reason why we want to define the functional unit is that this advances net energy in the past, right? You would say it's energy unit divided by energy unit. So you could have megajoules divided by megajoules. What we're seeing, though, right, is that the megajoules on the top will be crude oil and the megajoules on the bottom might be electricity. So now you're dividing two vastly different resources, right? So it's incredibly important that we make comparisons of the same functional unit. And that also means the system boundary needs to be defined, right? What is and is not included. In some, to compare EROIs, we have to have the same functional unit and system boundary. And that really just got boring, and I'm sorry, I don't mean to be boring, but it's important that we understand that that is what the LCA community talks about, right? When they make comparative assertions, right? And again, it's not perfect out there, and there's definitely problems with the way in which it's executed in certain cases. But what the methodology stipulates is that to make these comparative assertions, we have to make sure that these study design parameters are the same. And that is actually what's been written in the net energy literature a lot, right? You got to explicitly state your boundaries, explicitly state like what you're calculating. Well, really just explicitly state your boundaries. We don't have something called a function unit in the NEA literature, but what the LCA does is just kind of give you some ideas on how to gives a explicit methodology on how to define that boundary. So much of the EROI literature violates these basic rules for comparisons, right? And this is where it gets confusing in the literature, right? So this is that figure I showed you earlier from Hall and Day, and we put this in our 2016 analysis, right? So if we pull out just the major energy resources here, coal, hydro, wind, natural gas, conventional oil, solar PV, and corn ethanol, these are the actual units that are being calculated when we do these analyses, right? So for coal, it's generally calculated at the mine mouth. So we can think about how many megajoules of coal are produced at the mine mouth. How many megawatt hours of hydro are produced at the facility gate? How many megawatt hours of electricity at the turbine gate? How many megajoules of natural gas at the well gate, right? And so on and so forth, right? These are all different units of analysis. So it's functional unit mismatch. And this right here, this is from my early work, right? It has a boundary issue here, okay? So we talked about the different types of resources that are included in this, but what does that mean in terms of the EROI calculation? Well, oftentimes it means there's a boundary issue. So this is a simple diagram from our 2022 paper with primary energy source over here. Let's say that's crude oil underground, something like that. We extract that and we get a primary energy production process. So this is like the first thing, pulling energy out of the ground. There's a little bit of an investment cost for that, right? And we can calculate an EROI here at the point of extraction, system boundary. If we refine that a little bit further and process it, we can make that into an energy carrier here, okay? This would be at the point of use. That energy carrier is now consumed by society. So this is the difference between crude oil and gasoline, right? Gasoline has to be transformed and then is used by society. The problem is in this up here, we have crude oil up here, but we also have electricity up here. Electricity is at the point of consumption, right? Electricity is not at the point of extraction. That would be sunshine, right? Coming into a PV panel. So on this graph here, we have these different resources, right? They're all measurable in megawatts, but they have fundamentally very different boundaries of analysis, right? So those were some of the issues that we were seeing in the literature. And that, now that I'm like 30 slides into this presentation, that was just like, that was all the background for why I wanted to do the 2022 paper called EROI, Energy Return on Investment of Major Energy Carriers Review and Harmonization, right? So there was all this literature out there, and we wanted to say, like, listen, can we go to the literature, make sure all of these literature values have the same boundaries, the same functional unit, and then see what the numbers show. So we did this meta-analysis from 2017 through 2020. We reviewed 113 papers. We went through each paper to determine the methodology used and to see whether harmonization was even possible. There's a bunch of IO analyses, that's input-output analysis, that is fundamentally like a very different methodology than process-based analyses, which is what most of them were. So we couldn't use any of those, right? So, and 113 papers was not the universe of papers. There's a few that were left out, unfortunately, that we didn't mean to leave out, but they just didn't, for some reason, come through our scan. It wasn't never intended to be the universe. We just wanted a large sample size to get some EROIs in there. But you can see, after tallying the initial tally, the post screening, we had to reduce the papers quite a bit. And then we took them in a spreadsheet and we went through and we looked at their parameters and we tried to harmonize them. And we harmonized according to basically the functional unit and the system boundary, okay? And we tried to make sure that all measurements were measured or we did make sure that at the point of use. So I think there's value in measuring EROI at both the point of extraction and the point of use, but I think in terms of economic performance, the point of use is very helpful because that's the point at which all the energy is being delivered for consumption. And I'll show you why I think point of use is perhaps a better indicator for economic health in a minute than point of extraction. What we have here in this diagram is energy sources on the left with the extraction, right? So a lot of our research that we looked at the metadata will start right at that gray box there at the point of extraction. And what we did was go to the EcoInvent LCI database. This is a huge database that's globally used, and come up with global average processes for preparation, transmission, refining, purification, distribution. And not all fuels use each one of these, but for example, oil has to go in a pipeline and that's under transmission. So we looked at like an average cost of an oil pipeline. And if we had a paper that reported crude oil at the point of extraction, we would then add the data and the energy cost to transmit it, to refine it, to get it all the way to the point of use. In other words, to add it to get there to gasoline. So the thermal fuels were the ones that we generally harmonized using this graph right here. Electricity was different, and we have two separate figures I'll show you in a second for thermal fuels and electricity because they're fundamentally different things for society. And they're utilized differently, the different functions. The harmonization for electricity was ensuring that the fraction in the EROI used primary energy on both sides, because oftentimes when you produce electricity, right, you're producing something in kilowatt hours of electricity. But then you end up, and the denominator, the energy cost, is often measured in megajoules of primary energy. So we convert the top, the electricity, into primary energy equivalents so that we're doing, how we have the same units on the top and bottom. So let's look at some of the results here. The results were a little surprising in that most thermal fuels we found had an EROI at the point of use that was below the net energy cliff threshold, right? So this is I'll point out, this is a busy graph. Let's start on the bottom here. We have EROI on the bottom. We've put this gray line in here because that's the threshold, right? So just think like if you're to the right of that, the resource has enough net energy. If you're just to the left, it's a little bit below the threshold and maybe it's okay. If you're really far over to the left, it's a problem. And 1 is right here. So that's like, that's basically there's no net energy. Below that is an energy sink. So that's how we interpret it. Let's start on the left side now. So we have fuels, gaseous, liquid, solid. And remember, this is all thermal fuel. So these all get burned at some point, right? And then we have the carrier, which is gas, diesel, ethanol, gasoline, coal, wood chips, just further kind of refining. And then this is kind of the resource that produced them, right? So the primary energy source. So this, I'm gonna point out a couple here that we want to pay attention to. So for gas, let's look at natural gas, right? So this is just conventional natural gas production. And what you see, this is really important, right, is one estimate in the literature below 10, one estimate way up here. But after we harmonize them to the point of use, right, that variation shrinks dramatically, right? And you get both values are right here below kind of that threshold. You could see the same trend occur down here. This is oil, this is gasoline production from oil. So we're thinking about the energy carrier, right? And we have this wide spread right here just below the threshold that gets, so that it gets narrowed a little bit and it reduced a little bit there. And the same thing happens with coal, a non-harmonized value, a harmonized value, okay? And we'll talk, I'm gonna talk in a second about that math and why that happens. For electricity, we found that most renewable energy EROI at the point of use are above the net energy cliff threshold. So kind of opposite. So let's look at a few here. Hydro, okay? Now, there's an interesting dynamic here. I'll walk you through why the math works this way, but this is the EROI just reported in the literature. This is adjusting for primary energy, these next two values. Now, what is ETA here? ETA is the grid efficiency. So if we produce a kilowatt hour of electricity from a PV panel and we want to convert that to primary energy, what we're saying is how much primary energy is required to produce 1 kilowatt hour of electricity. In our thermal grids today, that are about 30% efficient. So that's an ETA of 0.3. If in the future we modernize our grid systems and we use less thermal fuels, right, that efficiency theoretically can go up. So we wanted to represent that here as ETA 0.7. But when you divide 1 kilowatt hour by 0.3, it jumps it more than by 0.7. So what you get is a non-harmonized value, a big jump when you have a very dirty grid because it requires a lot of primary energy to produce it. And then that shrinks back down here with an ETA 0.7. That's just how the calculation works. But the point is also that it's above 10. And then we look at some other resources. Natural gas here is about 10, but when you harmonize, we don't have a non-harmonized value. So depending upon which grid system you're in here, right, the values change. PV, right, here are the non-harmonized values. Then in our current grid system, way up by 20, 30, 40. And then in a future grid system, still above 10. And wind is above the threshold the entire time. Okay.
Dave, before you move on, there's
Yeah.
a question that I think directly goes to those graphs, so I
Okay.
figured better ask it. Should we really define an EROI threshold, and do we really know what happens? Some clear change at EROI equals 10. And the comment is, I'd say no, we don't know this.
Yeah, I know. And that's what I was saying in the beginning. We use 10 because it's a round number. And I don't mean for these to be like, everything above this gray line is awesome and everything below this gray line is terrible. That's not the way to interpret it. I think I use the 10 because it's a round number. And I think that if we have EROIs above that, we're safe in a sense of like that, we're not going to have massive net energy losses to society. But what we would need to answer that question is a determination of what EROI, what the minimum EROI is for society right now or an industrial society. And the range, that question has been asked in the literature, and the ranges there are from 3 to 5 to 8 to like 15 to 11 or 12. So we're not, and those analyses are all very, very different. So it's unclear, right? That's probably not a great answer, but no, we don't want to. The net energy threshold should not be interpreted as like everything's great above that and everything is terrible below. Maybe I should have like a wider gray bar there. I don't know. But good question. Thank you for that. But I wanted to show one more thing here, which is why you get this shrinking effect when you harmonize these values at the point of use. And this is really important. There's going to be two graphs here that have just a little bit of math, and that's kind of what will end pretty soon. So I want to think about three different energy sources, right here. Let's say the first one has 1 unit energy invested, but produces 100 of primary energy. So at the point of extraction, we get an EROI of 100 to 1. This one requires 2 units of investment. 100 divided by 2 gets 50. This one is 4. 100 divided by 4 gives you 25, right? So we have 150 and 25 for these three resources. And they're represented on the graph here, 150 and 25. All right. Now let's look at harmonizing these at the point of use. Well, let's say for hypothetically, that each one of those has a refinery cost of 9. Okay, so 9 units of energy. Well, now the EROI at the point of use is 1 plus 9, that's 11, right? Or 10, excuse me, 100 divided by 10 is 10, all right? 2 plus 9 is 11. 100 divided by 11 is 9.1. And then 4 plus 9, right? It's 13. 100 is 7.7. So we get a spread from 100 down to 25. When we add the same energy cost at the second point here, now our spread is 3 units at the point of use. And it's a dramatic drop, right, in the EROI. We've only added 9 units. We're still producing 100, right? But the math of EROI works out as such. Okay, and I'll show you how this plays out when you calculate them at the point of use. So this table's in the 22 figure. There's a lot going on here, but we're going to walk through it very slowly. So this includes, you remember this figure I showed you down the bottom left here that shows these are the generic stages in producing oil, right, that we identified. Well, up here, they're repeated, and we have some energy data to go along with them to do the calculation. So let's say we start with a resource right here has an EROI of 10,000 at the point of extraction. Let's just say it's 10,000. We write it in here as infinity, but I can't do math on infinity. It's easier with 10,000. Okay. And let's say we wanted, okay, so we're at the point of extraction, we're at the wellhead. Let's put that oil in a pipeline and get it somewhere. So let's go to the next stage. So there's no preparation cost. I should have mentioned that for oil, right? This doesn't exist in the life cycle of oil. So we just throw it into this pipeline and we bring it somewhere. Okay. So we go to the EcoInvent database, and you can go in there and you can pull up transport pipeline onshore petroleum, right? So this is pipeline across land. And these are the energy costs to put oil 1 ton kilometer. And I'll show you, this also includes the cost of pipeline construction. Okay. You can see that it's times 10 to the 9th kilometers, right? And that's because it's amortized over the entire life of the pipeline, because the functional unit, or really the reference flow here, is 1 ton kilometer. So that's how much of the pipeline cost is spread out. Once you spread it out over the life, is allocated to 1 ton kilometer of oil through the pipeline, because billions of tons are going to flow through this pipeline over its life. So we bring that back and we find out that this investment of pipeline equals 1.5% of the cost of shipping the oil through it. EROI equals 10,000 divided by 10,000 times 1.5%. That gives us a maximum EROI of 67. So just including the transportation, we're down from 10,000 at the wellhead to 67, right? Just due to the math and the energy costs. Then we want to refine it. Refineries are pretty dirty, so we go to the EcoInvent. We pull out this huge refinery process here, and we can see all these energy components that we were interested in. How much energy does it take to run a refinery? And then these are all the emissions. For those of you that want to study the emission cost of this, like there's just all, this is what I mean. The data in LCA was way ahead of the data in the NEA community. And this kind of like blew me away when I was able to access all of this stuff. And the global process in the EcoInvent data says that refining oil is 8.9% of the energy cost of the oil that comes in. So we add 8.9 in here, and that means a total of 10.4 if you sum these two to get oil through a refinery. Okay. So now we have gasoline coming out, and the EROI of that gasoline is 10,000 divided by 10,000 times 0.104 or 10%. So that's a maximum EROI of 9. A theoretical maximum EROI of 9.6, even with an EROI at the wellhead of 10,000. So there's no purification costs in oil, but there are distribution costs, right? So now we have gasoline now, but it's not at the point of use because it's not at a gas station. So these next costs, right, are 0, 9.6 again, and then 1.1, we add that there. So we get an EROI maximum of 8.7 to deliver gasoline to the point of use from an initial EROI at the point of extraction of 10,000. And that is why the point of use calculation, I think, is so important, because of the way we calculate the EROIs, right? You get these energy costs, you add them in there, and it shrinks down the variability of these estimates quite a bit. All right, so I'm done. Basically, I just want to say some conclusions and caveats, and I'm happy to hang around and answer questions. The EROI at the point of use indicates the energy returns at the point of consumption for the economy. And as I said, I think I prefer to use that as an indicator of whether a technology is going to add net energy or not. Because if you do it at the point of extraction, as I just showed, you're omitting those steps in the middle. And depending on the technology, those steps in the middle can make a big difference. Comparing EROIs, if we want to compare them like we did in the harmonization project I just showed you, right? We have to compare the same functional unit and use the same system boundaries. Otherwise, it's simply an invalid comparison. So we can't compare electricity with gasoline. They're two fundamentally different things. But what I like about the LCA framework is that you can still make that comparison. You just have to find a functional unit that they both share. So for example, you want to compare electricity and gasoline, what you should do, right? And a lot of people have done this, right? Is compare one vehicle mile traveled, right? Make the functional unit a vehicle mile traveled, say a medium sedan vehicle or something, and then compare the energy cost of that vehicle mile traveled in an internal combustion engine and a battery electric vehicle. And you can look at the entire upstream cost of producing the battery electric vehicle and producing the internal combustion engine. And you can get the energy costs of doing that. And that way your boundaries are the same. Your functional unit's the same, right? We can't compare crude oil with electricity, right? Those are different primary energy versus energy carriers. EROIs for renewable energy do not indicate a sudden sharp decline in net energy to the economy. I know that there's this contention by some that there's no way that renewable energy can replace fossil fuels. For all I know, they may be right. There's a bunch of reasons, and if you're paying attention at all to what's going on in the ISOs and RTOs and stuff that's happening in the electricity world right now, maybe it's going to be a lot harder than we think. I just don't think energy return on investment is going to be a force that's going to stop the transition. I see PV and wind as producing enough net energy, at least at the point of use. I'd also like to address one other question that has come up, and this is in the literature and in a lot of places, solar and wind are intermittent sources of power, which require backup systems to support grid resiliency. So aren't your estimates incorrect or at least misleading, right? Like, what about the fact that these are intermittent sources of power? I guess I would answer that in two ways. The first one I would say is that that's not really how the grid works, right? Balancing authorities are responsible for grid resiliency, and they accomplish that through a number of different measures, one of which is power production, but not the only one. I cannot think of one balancing authority in the world, one grid system, where resilience or balancing of that grid system is assigned to one generator, right? Which is essentially what we would be doing if we did an EROI and added all these backup systems to a PV facility so that it can have 24/7 power 365 days a year. You're essentially assigning the balancing of the grid system to that one PV system. And that's not how resiliency in grid balancing is done. And I would also say that like all the generators on the grid benefit from the balancing from all the other generators. So it is a totally different dynamic. It's not an easy question to answer. And the other thing I would say is that measuring grid balancing requirements, it actually changes the functional unit of analysis, right? And so it would require kind of a new analysis. So it's like instead of all of our analyses I showed you are production at the point of consumption as we define entering the grid. If we want to look behind the grid, right? 1 kilowatt hour consumed at a house or something like that, that's fine. But then you'd have to have different grid systems with different mixes and count all of the upstream costs of producing all the technologies that are in there. It's certainly done. It's actually an analysis I'd be really keen on doing. But it's not as simple as all I'm saying is like taking PV and being like, okay, PV is intermittent. It's got a capacity factor of 15. So we're going to have to put, 4 weeks worth of battery backup systems for every panel. And that's not an appropriate way to do that comparison. So anyway, that was a lot. I feel like I spoke way too fast. I'm sorry. But that's all I have for you. And thank you all so much for taking time on, well, at least it's beautiful up here in upstate New York today on this nice day. And as I said, I'm happy to answer any questions. Wait.
Thank you, Dave. That was very interesting and a lot of great information. So we'll open it up for questions and comments. There's one already in the chat box by Jeff Organ. Jeff, I could either read it or you could ask it yourself if you'd like.
Sure. Yeah. Good to see you again, Dave.
Hey, Jeff, how are you?
Stayed the course with this research over time. I've moved into renewable energy as a practitioner for the last 18 years, so I'm definitely interested in these topics. But yeah, one of the interesting things that I think it came up actually in green tech media a while ago as a potential criticism of some of Hall's work was that at least on solar, was that it didn't account for the potential scale of deployment of solar over time, and that, perhaps that even though solar might have a lower EROI, if you deployed so much solar, maybe you could cover 10% of the earth with solar, there's so much marginal energy that maybe the EROI metric in itself isn't important or as important. So I was wondering just like what you've seen on this in your research or in the literature, as far as scale and do you think that this is something that should be incorporated into these analyses as well as boundaries and point of views?
Are you talking about like the pace at which we deploy lower ERI resources and whether or not that's going to influence net energy flows? There's definitely been some work on that. I know Inigo Capellan Perez has some work out of Spain, and that indicates it's definitely a problem. Mick Dale also published something a while ago. Carrie, you may have something on that too. I don't know. And so there has been some work on that. I just don't, to get significant net energy declines, the EROIs have to drop significantly, right? So I don't know how that plays in, all the time, I guess is an answer. I don't know. That's not a very good answer. But that's all I have right now. Inigo has definitely done some work on that. Basically what we're talking about is like you invest so much energy in building something, there's like all this energy is going to this, but you're not getting the returns from PV for 30 years, right? So those are amortized over 30 years. So the net energy comes off of that very slowly. It's really more analysis of power return on investment that has been done as well. I didn't answer that question very well, Jeff. I'm sorry. It's good to see you again.
Likewise, no, that's helpful. Thanks.
Carrie?
Yeah, I guess I have this has a question on the sort of harmonizing thing and maybe particular electricity. So the I'll state one thing on the grid balancing services. Maybe not for you stated that there's no grid operator assigning grid balancing or ancillary services or something to a particular generator. People are trying, but I would say at least it's applied to a class of generators to quantify certain quantities of ancillary services. Like if you have this much wind, then they'll increase the spinning reserves in
Mhm.
ERCOT, for example. But on the harmonization, so I've always kind of struggled in my head with the primary equivalent thing.
Mhm.
But so before you apply a primary equivalent, would it be, is it correct to say that your EROI you're calculating for electricity is effectively a kilowatt hour divided by a megajoule of heat?
Kilowatt hour of electricity divided by a megajoule of heat before we do the harmonization.
Well, even after the harmonization, but before the primary equivalent denominator. And so the primary,
Well, our harmonization was doing the primary energy equivalents for those
okay,
electricity. So it would just be
right,
EROIs that were calculated looking at electricity coming out and then thermal, megajoules of heat kind of being used in the
going in.
denominator.
Yeah, and so the purpose of the primary energy equivalent is now to, well, essentially multiply the denominator by kilowatt hours divided by megajoule of heat. So you end up with an EROI after the primary energy equivalent of megajoules of heat divided by megajoules of heat.
Exactly.
And so those are the same, but now it's not even electricity anymore.
No.
So it's a weird kind of, I don't know, it's just, I find that, so I find it conceptually
You can
difficult.
harmonize the denominator if you want to electricity. The point is you have to keep them in common units. And I think the convention has been to do it this way because the cumulative energy demand function that so when you use the LCA software and you calculate how much energy it takes to produce a product or something, they do that in cumulative energy demand, and cumulative energy demand backs all of the costs up to primary energy units, right? So it takes, even if the energy unit is used like somewhere midstream in the production process, it's calculated at the primary energy point, or like when the analysis comes out, it's brought back to the primary energy that comes out of nature. So we have primary energy units almost all the time in the denominator. So it's just a way to make the numerator similar to that.
Right. So given that, so yes, I'm agreeing with what you just said there.
Mhm.
So given that understanding, a photovoltaic panel doesn't use heat to generate electricity. So is it consistent to convert its output into a heat equivalent?
What do you mean?
So you're giving a characteristic of the grid to a photovoltaic panel. I'm just using a PV panel, for example. But a PV panel doesn't have the characteristic of converting heat into its output, which is a kilowatt hour.
Mhm.
So I was wondering if it's better to always just say, we're just going to compare kilowatt hours divided by cumulative energy demand, or kilowatt hours divided by megajoules of heat.
Well, I mean, I think the idea here is that, and there's another issue that is probably debatable, and that is like how much primary energy is required to produce a kilowatt hour of electricity from a PV panel, right? But the idea is that if that kilowatt hour weren't produced from my understanding at least, right, from the LCA, is that it's this replacement cost kind of like mentality, right? So if that kilowatt hour were not produced by the PV panel, it would be produced by the grid system, right? And the grid system in a specific location has a certain heat rate average. And that's where ETA comes from, right? So that ETA will change. We use 0.3 and 0.7, but that ETA changes, and the databases have estimates for ETAs all around the world, right? So the ETA will change depending on the specific heat rate of that grid system. And so it's that kind of replacement logic, right? So if we took this kilowatt hour from away from PV and we assigned it to just the grid producing more, we would use that heat rate. I don't know. I mean, I think it's fine to do kilowatt hours divided by megajoules. You just get something totally different. And if you want to use that analysis, then what is the corollary if you want to do a comparison, right? Like, what's the corollary for something else, right?
Yeah, it's a good point. I'll just point out on this and then shut up. Yeah, so the EIA, I think you're probably aware, last year or the year before, I don't recall, they actually converted to understanding the primary energy content of, let's just say PV electricity, or as equal to 3.6 megajoules. And the US used to assume this primary energy equivalent type thing. So in that sense, the world is converted to say that a primary energy content of 1 kilowatt hour is exactly 3.6 megajoules, which would not be dividing by a PE of 0.3 or 0.7. So anyway, thanks.
Well, thanks, Carrie.
We have a few more questions. We'll go first with Christina.
Hello, can you hear me?
Yeah.
Amazing. Yeah, thank you for the presentation. It was really interesting because in here I hear often that EROI is kind of used by degrowth scholars a lot to kind of argue that the decarbonization of the energy system is not possible. And I have two specific questions that I don't really understand. One is, and you mentioned it, like, you know, like how do you measure or how do you like conceptualize the ROI of a society or of like the not of the like energy production, but rather like the ROI that is necessary for a specific like economic system or like a city or anything to have? Because I don't really understand, you know, like what is really behind this. And the second thing, and I think it was mentioned with the like factor of 10, but the second question is like, as I understand it, like if we take an organism and say, okay, the organism is able to like take, you know, like to put a unit of energy and kind of get 2 units out of it. So like basically the ROI is like positive, it's like more than 0, and you can work with it, you know, you can kind of like you're not below 0. And then what it really brings me to is that it's not really important what the ROI is, but the thing that is really important is what's behind it, you know, like either it's like labor, you know, like if it's inefficient, it's like time consuming, or it's maybe like materially consuming. And I guess that's a big question for the renewable energy, for example. But like it's not the like energy efficiency in this like sense that matters. It is really like the efficiency of like the input, like what this kind of like electricity takes in terms of other inputs that you have to put inside of it, if that makes sense. So yeah, I just really wondering about like the economic systems and what like the EROI is and what the conceptualization is. And there also like if you're thinking about like the material and labor footprints behind the EROI.
Right. So thank you so much, Christina, for the question. If I can just reiterate them just so I understand. The second one would, I think, doing the second one first, it sounds like you're asking whether or not EROI considers the differences in the quality or the type of material that go into the calculation, whether it's electricity or you know, even just materials, right? Like silicon or crude oil or whatever it is. And the first one is, how do we figure out like where society requires an EROI? Like what level is, how do we go about thinking about that? So the first one, the quick answer is no. Like EROI doesn't necessarily look at depletion and how much is left. And that's where you have to do, like you can incorporate EROI in some modeling that has how much reserves of different resources are out there. But the metric itself is kind of agnostic to how much of a resource there is in the world. And EROI in general wouldn't include any materials. It would just be energy. And there's a lot of permutations in the net energy literature of, I'm talking just about energy return on investment. There's a bunch of different net energy metrics that can be used. Kerry's probably a better person to answer the society question. He's done a ton of work on that. So is it okay for like I'm the host, but for me to punt the answer to Kerry, is that like all right to do?
Sure. Not a problem.
As part of my question to Dave, I'm going to put a link in the chat in which I wrote a blog that uses my macroeconomic model, at least say why answering the question of what's a minimum EROI of society or how does EROI relate to the structure of society in general, a hard question, and that you might have to have a macroeconomic model to answer it. So I'll put a link in there. But the short insight or potential insight is it's sort of if you take away wages from people and make them poor or turn them into slaves, then you sort of have energy they would have maybe consumed to install more capital and infrastructure. And so you can have a lower EROI and still have a society that functions, but it's less equal. So I think these kinds of things are linked together. But yeah.
The other thing I would say is I wrote a paper with Tom Murphy. We haven't published it, but EROI can go down. Like the examples I gave in my presentation of 100, 100 comes out and this much in energy comes and then 100 and this much. They're all bound by how much, like I kept 100 constant. When you go to PV, and this is totally theoretical, right? Like if we go to renewable energy resources, there's vastly enough PV in the world to power. Like we all know that, right? The insolation level that hits the earth is more energy by, 10,000 times than we actually consume as an economy. So if that's the case, right, you can have EROIs that are really low, that deliver small amounts of net energy because you have almost infinite extraction of energy. But that's when you come into environmental degradation and other limitations, right? Material constraints and things like that. So energy isn't going to be necessarily the limiting factor by itself, but all those other things do add up.
We have two more questions. Roque, go ahead. Hopefully I pronounced that right.
Thanks a lot. I hope you can hear me.
Yes.
Yeah.
My question is related to adding batteries into the system or other storage. I have another question related to the timing, so that in the transient, the EROI is more important than the whole lifetime. But maybe you don't have time to go into that. So let's stick to the first one.
What exactly is the question with storage?
Well, you're not considering it in case of wind or photovoltaics.
Mm-hmm.
But what if you want to add it? Say you put a battery system at the generation site, co-located. Have you tried that?
I personally haven't, but there have been studies that have done that. I think Marco Rauger has published at least one, if not a couple studies that measure PV plus battery systems and measure the EROI of those systems. And it didn't markedly change any of the outputs. What was the other question about timing?
You're considering the whole lifetime of the system, but not the transient. But it could be the case that for low EROIs, you are asking the society to give a lot of energy in order to that happen, and that could be more important than the final EROI balance.
Yeah, no, I mean, I totally agree with that. The question I think is where that line is, right? And it's very clear to me that like your resources that are very low EROI, that are below 3, let's just call it 3, are really struggle. Biofuels are kind of the poster child for this industry. I have nothing against biofuels. I'm just saying on the energy return side of it, corn ethanol in the United States is a highly mechanized industrial process. But that industry still, 15 years later, is heavily reliant upon government support and the blending mandate for survival. And it's just that the underlying, just like thermodynamics and chemistry there are limiting, right? It's that the profitability isn't there. You can kind of look at hydrogen and think, where's that going to go as a resource? Hydrogen is an energy carrier. That's not so to produce hydrogen, we first have to produce, well, if we want to do it through electrolysis, we first have to produce electricity. So we're starting with an EROI, depending on the grid system, of anywhere between, I don't know, 8, 7, and like 15. So you're already starting, let's just call it 10 with an EROI there. And then you have all you have from there are costs to get to hydrogen, right? So the initial calculations that I've done for that are that the EROI of kind of like large scale electrolyzers, that kind of thing is very much close to 1-to-1. So I wonder how that's going to scale, right? And what generally happens, to your point, do you pronounce it Roquet? Is that correct? That what generally happens in these industries, right, is that they consume a ton of energy, and it's kind of like the Red Queen. They keep spinning and spinning and spinning, but they're just energy in, energy out. Everything's the same. There's no net profit there. So they tend to be energy sinks over time.
And we have just one last question. This is from Gabriel. I think he's online. You want to go ahead, Gabriel? Okay, I'll ask. Can this solar analysis be effectively deployed in developing countries like Nigeria?
Yeah, it can be deployed. I mean, LCA can be deployed in any country around the world. Net energy analysis too. It's a question of data, really, to make it bespoke to whatever the system under study is, for sure. No, that would be very interesting. Definitely.
All right. Dave, do you have any last comments or anything?
Parting words. No, no words of wisdom today. I really do appreciate it. Jeff, it was good to see you again. Carrie, thanks for bailing me out on a question there. And if anybody wants to get in touch, I'm at St. Lawrence University. I'm more than happy to continue chatting. If I didn't answer your questions or you have them and you're feel like you don't necessarily want to ask them in this venue, please feel free to reach out online and just email me. I guess I can put my email in the chat. That way you don't have to like search for it. But that's it. So thank you very much, everybody.
Well, thank you to everybody attending. Thank you especially to Dave for a wonderful presentation and a lot of information. So it's great. So can't thank you enough for doing this and taking time out of your schedule. And just would like to remind everybody, our next seminar will be May 17th by Corinne Lindberg, also at noon Eastern. She's one of the originators of ecological economics, and I'm sure it'll be very useful to you. So hopefully you can all be there. And once again, thank you, Dave, for doing this and your very thought-provoking seminar.
Thanks, everybody.
Thanks,
Have a great day.
Hi, Dave.
See you later, Carrie.